Hello friends, welcome to Learners Forum. So in last video we saw about what is a basic rectifier and certain characteristics about a rectifier. So from this video let us see the types of rectifier starting with half wave rectifier. So from the name itself we can understand, we know what is a rectifier. It converts an AC signal into its pulsating DC. Half wave in the sense only one half of the cycle will be rectified in this particular type. So when we consider the two cycles, positive half cycle and negative half cycle, in half wave rectifier only the positive half cycle will be rectified. That is, only when we have the positive half cycle the respective AC will be converted into pulsating DC, whereas in the negative half cycle the signal will be simply eliminated. So we will have rectification process under the one half of the cycle. So looking on the basic circuit diagram, we will have a source of AC voltage here. So here we will use either a step up or an step down transformer, but mostly step down will be used. So here we will get the required AC voltage. So that is applied across the particular rectifying element, which is nothing but a diode. And after this particular rectifying element, it is passed into the resistive load. That is, as we have seen before, we will be connecting a resistance in series along with the load. So we have taken a load resistance over here. So here we will have a single phase AC supply as a source of AC voltage, and here in the rectifying element this AC voltage will be supplied to the particular diode, which is having an forward resistance of RF, and third part will be the resistive load, where we will have the voltage across the particular element as EDC, and the load current flowing here will be IL. So this is the basic construction of a half wave rectifier. So we will have all the three elements, that is the source of AC voltage, rectifying element and resistive load, to be connected in a series way. So using a suitable step up or step down transformer, like I said before, mostly step down will be used. Here the AC voltage is applied to the rectifier circuit. So this half will be the rectifier circuit, and the applied AC voltage will be sinusoidal with a frequency of 50 Hz over here. So this is the basic construction of a half wave rectifier. So here the transformer that we have used will decide the peak value of secondary voltage, which is given by N2 by N1. N2 refers to number of turns in the secondary winding and N1 refers to the primary winding, which is equal to ESM divided by EPM, where this ESM and EPM refers to peak value of primary and secondary AC voltage, and N1 N2 refers to the number of turns. So this particular voltage ESM will be sinusoidal. The instantaneous value will be ES, which is equal to ESM into sine omega t. So like I said before, the value of RF is nothing but the forward resistance. So this is the basic construction of a half wave rectifier. Now let us see the circuit operation, that is the working principle of a half wave rectifier, how the positive half cycle is rectified and how the negative half cycle is eliminated. So under the circuit operation, we can divide it into two cycles. So what happens when it is in the positive half cycle, and let us see what happens in the negative half cycle. So whenever we have positive half cycle, the diode will be under forward biased condition as we have seen earlier, and the current will flow in clockwise direction. Whereas in negative half cycle, the diode will be under reverse biased condition. So the common thing is, whenever the diode is in reverse bias condition, there will not be any flow of current. That is, it will act as an open circuit. So the total load voltage will be equal to product of load current and load resistance. So when we know the values of the two things, either current and resistance, then we can calculate the voltage, or in case if you need to calculate the value of load current, knowing the values of load voltage and load resistance, you can use this relation. So looking at the circuit operation, we can identify how the positive half cycle is converted into its equivalent pulsating DC and how the negative half cycle is getting eliminated. So this is the basic circuit of a half wave rectifier. So here we are applying a positive half cycle. So here it is having only the positive half cycle, which is applied to the transformer, and through this we will have an AC voltage applied to the rectifying element, which is nothing but a diode, which is mentioned as D here. So A and B will be the terminals over here. So whenever we have positive cycle, the terminal A will be positive and the terminal B will be in negative value. and it is applied across the rectifying element diode, and then we have a load resistor which is connected in series. So under this condition, the diode will be in forward bias condition, and we will get the same kind of positive half cycle in the load resistance value. That is, we will have the equivalent DC value. But whereas when we consider it for a negative half cycle, when we apply the negative half cycle to the same kind of AC voltage, that is, we have a AC voltage supply here, and then it is moved into the rectifying element. So when we apply negative cycle to the same first half of the circuit, here the diode will move into the reverse bias condition, which means it will not conduct. So we will have an open circuit over here. Since it is open circuited here, the output value of voltage will be 0 volt, since there is open circuit connection. So this is what happens between positive half cycle and negative half cycle in an alternate manner. Looking into the waveform, we can consider a basic AC voltage signal. So here we will have the secondary voltage ES value with the maximum magnitude of ESM. So whenever the diode is in on condition and off condition, you can see the narration over here. So during the positive half cycle, the diode will be in on condition, and during the negative half cycle, diode will be in off condition. Like I said before, similar thing will be getting repeated for every half of the cycle. So again we will have a positive half cycle, so it will be under on condition, and for the second half cycle, that is in the negative half cycle, diode gets turned off. So whenever this process occurs, we are calculating the value of load current and load voltage now. Load current in the sense we are calculating here, which means whenever it is under positive half cycle, the diode will conduct, so we will get the required value of signal over here. Next, it is under negative half cycle. So whenever it is negative half cycle, the diode will be under open circuit condition, so we will get a 0 value. So it will be just a straight line. And again we have a positive half cycle for which the diode conducts, so we will get the required same amount of signal. So there will be a positive signal, and when it is in the negative half cycle, again open circuiting condition, so we will get a 0 value represented by a straight line. Next is load voltage. So when we calculate the voltage across the load, it will be similar to the condition of load current. So we can use the equation directly instead, which is nothing but load voltage, which is equal to load current into load resistance. We know the value of resistance and we know the value of load current also. So whenever we will have the value of load current, we will have the value of load voltage also. So again it is represented with the same waveform. So here we have a maximum value of Im. So here we will have the corresponding value in terms of voltage. So here it is 0. So for the second half of the cycle, again the load voltage also will be 0, because even if the value of load resistance is finite, here the load current is 0. So 0 multiplied with any finite value of load resistance will be again 0. So we will have a same waveform like the load current also. So this is the waveform for load current and this is for load voltage. Now let us see what happens when we calculate the voltage across the rectifying element, that is diode. So I have said before, when we saw about the characteristics, that is when we are calculating the voltage across the rectifying element, we will have a voltage called as peak inverse voltage. That is, whenever it is reverse biased, we will still have a reverse voltage value having a maximum value. So that peak value which happens whenever the voltage is reverse biased is termed as peak inverse voltage. So whenever we are calculating the voltage across diode, it will be just opposite to the value of load voltage. So here reverse biased in the sense, here you will not have any conduction, which means here we will have a 0 value, whereas during the negative half cycle it will have a small peak value representing the reverse voltage. So when it happens in the negative half of the cycle, we will have a waveform in this way. Again for positive cycle it will be 0, and for negative half you will get the waveform in this way. So make sure that you understand the waveform very clearly. For load current and load voltage, it is calculated after the rectifying element, that is after the diode value that we have seen in the circuit diagram. But this is calculated across the diode itself. So that is the reason we are getting an alternative waveform when we compare to load current or load voltage. So this is the working operation of a half wave rectifier. So before starting with the complete detail about the rectifier, I said how it is differentiated based on pulsating DC and DC signal. So the DC output waveform is nothing but a straight line which happens only when it is in ideal condition. But the DC output waveform, when we consider for practical condition, will vary, which will have positive sinusoidal pulses. That is, for ideal condition we will get the waveform, that is the signal in this way, whereas in practical condition we will get for half wave rectifier as this one. This is nothing but sinusoidal pulses, that is positive sinusoidal pulses, which is nothing but it is a kind of pulses, but here it is a kind of a DC signal, so we call it as a pulsating DC, which is nothing but a discontinuous signal. AC will be a continuous signal and DC will be a discontinuous signal. So this is for ideal condition, but for practical condition we will get in terms of positive half pulses, like we have seen just before in the waveform also. So this is nothing but a pulsating DC and DC signal difference. So that is why we define a rectifier as a device which converts an AC signal into pulsating DC and not just a DC signal. So this is the ideal and practical condition difference. So make sure that you know the difference between what is a DC signal and a pulsating DC signal.